Henderson-Hasselbalch equation is one of the first equations that you probably memorized from Chem 2. There may be others that you worked with, but this is probably the first one you really thought you had memorized and had a strong handle on. And if you remember from that, we made it the point that it's for buffers, and in a buffer you have to have your acid form and your base form, your conjugate base, of the acid present in solution at the same time. It's only appropriate for buffers. You must have the conjugate base and the acid at the same time in the same place. I'm repeating that a lot, and I know it. But a lot of people still make mistakes and try to use Henderson-Hasselbalch all over the place. Don't do that. If you're not positive that you actually have a buffer and it's an appropriate use of Henderson-Hasselbalch, go through the ICE table anyway. You'll still get to the same answer if you could have used Henderson-Hasselbalch, and if it was a case where you shouldn't have, you'll be safe. So be very careful. Now, let's take a look at one of the big powers of the Henderson-Hasselbalch equation and why buffers are so useful. And for that, I'm only going to expand this second half of the term, just to highlight what we're talking about. Now let's take that A minus and convert that to be moles of A minus over volume. And on the bottom, I'm going to do the same thing. Now hopefully you recognize that, yeah, that's a totally legit thing to do. All I'm doing is expanding the concentration to be moles divided by liters. But I wanted to highlight something. We're not talking about this being in one beaker and this being in a different beaker. These are in the same beaker, which means the total volume is going to be what we're using for both of these. Now you might be saying, oh man, you mean by mixing the two things together, now I've actually got to calculate moles and add the volumes? No. Here's why. Notice volume. This is going to cross-cancel with this. So in the Henderson-Hasselbalch equation, I can just put the moles of A minus on top and the moles of HA on the bottom. That's nice because we don't have to care about it if, suppose, in the process of a reaction, I added a little bit of DI water to it. Or if it's titration, I don't have to worry too much about pH drifting as the surrounding water comes from my burette and into my beaker. Not a big deal. It's all about the mole-mole ratio. At least that's our first pass at this. But let's be a little bit more rigorous. We know that instead of concentration, we really should be writing activity for all these. So let me go ahead and write out the activity. So I have log. Now we're going to have our activity coefficient of whatever species is A minus times the concentration of A minus. Remember, that's going to be activity equals activity coefficient times concentration. I have to do the same thing down here on the bottom. So for that, I'm going to have the activity coefficient of my undissociated species, and I'm going to have my HA. Now, as long as these don't change very much, one versus the other, I'm probably okay. And going one step further, when I change the volume that I have things, if they don't change much, I'm probably still okay. Now what do I mean by that? When I'm diluting, let's say I started out with this one originally, and then I'm diluting, let's just say 100x. Now that process should create a measurable difference, because I'm probably going to have a big enough change in my activity coefficients that I'm actually going to see this ratio start changing. So when I dilute that much, I'm probably going to have a problem. So that's something I would have to be more rigorous and actually include my activity coefficient if I really want to be very careful with it. Other thing I'll point out is if these numbers are very close together, suppose we're talking about H plus and we're talking about A minus, let's just pick one of them. Let's say we're working with, let's do citrate. And let's use the other citrate ion. Citrate 2 minus. Notice that we are going to go from this one to this one. We're going to have big differences between our activity coefficients if we're worrying about citrate as the buffer that I'm using. If I'm just working with something that's a lot more simple, I probably won't have activity coefficients making a big problem. So that's something we always need to be cognizant of. Are we actually going into separate charge states? That's a good sign activity coefficients are going to be different. So going from a -1 to a -2, that's going to be a sign that we need to actually treat for activity. It also means that dilution is probably going to have a bigger effect, because look at how big the difference between the coefficients becomes when we go from dilute solution to concentrated solution. This is about double. This is nowhere near double. So those are the cases where we have to be careful with our Henderson-Hasselbalch equation. If we're neglecting activity, we can generally ignore volume, but we should always be aware of that. Now, what does that mean for us in practice? It means that most of the time we're going to calculate what we want to mix together for our buffer. Then we're going to stick a pH meter in it. Then we're going to add a little bit of acid or base until we get it titrated to the actual pH that we want. That's how we really make a buffer. So mix, measure, and adjust.